Thanks so much, and I really appreciate the invitation to be here today. So I'm giving this talk for my former PhD student, Madison Decker, now Wozniak. So Madison has now gotten a job at FMC, and I hope I can answer all your questions. But yeah, so if not, we'll ask Madison. How about that? I'll send her an email. So I wanted to start by giving an overview and kind of the background of our project, right? So I want to set the stage so that you understand why this is important to look at alternative practices for weed control in conventional soybeans, right? And I realize this is an organic conference, and I'm surprised to be invited to speak here today because nothing I do is organic. As a weed scientist, I'm heavily involved in herbicide resistance evaluation and testing, but I am trying to put in more ecological tactics to help manage that resistance across the landscape. So integrated weed management is really the focus of my lab. And we don't want to see tools taken away, right? We want to have still herbicides as a potential tool for use in situations where needed, but we really need to diversify. And I'll make that case as we go through, but you all probably already agree with me. So what is integrated weed management and why do we need it? So I want to start with an herbicide resistance update for Illinois. And then how can we use wheat as a tool for integrated weed management? And it's all about crop rotations. And if you missed Carmen Blubaugh's excellent presentation on weed diversity just now, then she gave an excellent case for why we need crop rotations. I want to talk a little bit about allelopathy and then Madison's work on interseeding, and then I'll finish by talking about how we use Madison's work as a basis, and we got this SARE grant to then put her work out on farm. So integrated weed management is just this integrated approach that can steward technologies, right? So for the chemical industry, this means that they spend 10 years and more, hundreds of millions of dollars to develop technologies, and then they go out on the landscape, and without the necessary diversity to steward those technologies, they quickly break and we develop herbicide resistance. And that's what we're seeing over and over again, that we're putting too much pressure on these technologies, so we have to diversify. Some ways that we could do that is, harvest weed seed control, if you're familiar with weed seed terminators, electrocution, we've worked with the weed zapper some, cultural methods such as, my favorite, diversified rotations, and trying to see how we can put more diversity temporally into our cropping systems, but narrow crop rows, using cover crops or interseeded crops would fit within that. And then biological control. And right now, there's nothing that we can just purchase, right? There's no biological control that we can buy and release for corn and soybean systems. But we do know that by supporting crop diversity, then we can support the seed predators and the things that are going to help minimize our weed seed banks and reduce weed pressure over time. So I show this in every presentation that I give just to make the case that we're putting way too much pressure on herbicides in our cropping systems. But this is throughout the world, and this is all systems, not just cropping systems. So this is also your railroads, your rights-of-ways, all the cases where we use herbicide. You can see this exponential increase in the number of unique herbicide-resistant cases by time. So right now there are 534 unique cases of herbicide-resistant weeds globally with 273 species, and we have evolved resistance to 21 of the 31 known herbicide sites of action, and that's 168 different herbicides. So it's all selection pressure, right? We're spraying herbicides on a lot of different weeds, and we're selecting for that one individual on the landscape that has that resistance mechanism, and then that individual is reproducing, and then suddenly we have a resistant population that's spreading across the landscape. So if we look at what's happening in Illinois, these are all the cases that have been confirmed according to weedscience.org. There are other cases that are not listed here, but you definitely see why waterhemp is a major species of concern. It's an economic driver weed in our Illinois agricultural systems. So those are all the different sites of action that waterhemp is resistant to. Palmer is actually resistant to more, but outside of Illinois. And we may have those resistances in Palmer in Illinois, but they just haven't been documented yet. But you can see the list of species here. The numbers in red are currently resistances that we are documenting at SIU. So we've gone through the process of actually screening plants and confirming these resistances. So that's Liberty, our site of action group 10 for water hemp, and the PPO inhibitors, Bomesfen and Lactofen, if you know those, for site of action 14 and giant ragweed. And this is what our biotech traits have added to our ability to control, or I should say the herbicide selection pressure for the Amaranthus species in soybeans. So before genetic modification, we had very few pre-emergence herbicide options that we could use. and only one real post-emergence option, that was the PPO inhibitor site of action group 4. And then with genetic modification, those post-emergence options expanded to group 4, dicamba, 2,4-D, group 9, which is glyphosate, group 10, Liberty or glufosinate, and then now 27 HPPD inhibitors, which we don't see a lot of yet, but we will see that on the landscape starting in 2027 and 2028 with the new HT4 soybean crop trait. That's consequential because right now HPPD inhibitors are corn herbicides. So now we will see them used in both corn and soybeans in rotation, and that's going to drive further selection for HPPD inhibitors. And HPPD inhibitors are associated with 2,4-D resistance and metabolic resistance. So we will see increased selection pressure on herbicides, but we have to diversify. We have to put more things, more cultural practices in our rotations. So these are the screens that we've done. So I have been involved in the United Soybean Board project since 2015, but we've been doing this type of screening since 2018. What my lab does, we drive around the landscape at harvest time and we look for escapes of water hemp and palmer. And we collect those and we send them to our partnering universities, and they do a rough screen of a half X rate and a 1X rate of the three chemicals, 2,4-D, dicamba, and glufosinate. And then they tell us which populations look like we have a suspected resistance, and they send those seeds back to us, and we do a full screen, a dose-response curve to fully evaluate those populations. So that's where we are now. We now have identified some populations where we see definite resistances, so we're in the process now of working with those populations. So population 7 is from Saline County. That is now, you can see here our ED50 curves. So our ED50s on the y-axis there, that's the effective dose of herbicide that kills 50% of the population, and you can see that population 7 is way over that. So we have a highly resistant population to 2,4-D, up to an 8X rate, potentially. So this is dicamba. Even when we see suspected resistances to dicamba, our populations we're not able to confirm that in the greenhouse, but we know that we have dicamba resistance in Illinois, actually in this area. So, so dicamba, we also have that. Glufosinate, again, we see population number 7 is also resistant to Liberty or glufosinate. So that's a multiple resistant population now. We have 2,4-D and Liberty in that Saline County population. And then we have population 1 on the far right there, where that is a Franklin County population now. That is now, we're confirming resistance to Liberty or glufosinate in this population as well. So that's the really bad news, right? Glufosinate or Liberty was our last post-emergence option where we did not have resistance. And these are isolated cases still, but multiple universities around us are confirming this resistance as well. We're not the only ones. So you can imagine, you know, it's a result of the pressure that we're now putting on glufosinate because we're losing all of our other tools in conventional systems. So even though we're here at an organic conference, I'm telling you all of this because our conventional producers are now in the same situation, right? They're going to have to look at these organic tools and they're going to have to adapt and start learning how to do things a little bit differently to reduce the pressure that we're putting on herbicides. So this is just kind of a summary of our screens. In our southern Illinois populations, you know, we're still screening them, but we found that dicamba still controlled even our suspect populations. But we see that we have issues with 2,4-D and glufosinate for those two populations. And we see variability. So it's definitely not every individual, it's a small percentage of individuals in these populations. That signals to me that we're in the early stages of resistance evolution. So we're catching it before we see this spread throughout that entire population. So we have research that's ongoing because we want to screen these populations and see, you know, there's a suspected linkage between 2,4-D resistance and HPPD inhibitors, right? So we want to see, are these populations also resistant to HPPD inhibitors, for example? So we're trying to fully characterize these populations and their resistances. The great news here for everyone is that the seed bank longevity for Amaranthus species, so for the pigweeds, is pretty low compared to most other weed species. So if you can control these populations and severely reduce seed production for about 3 years, you've effectively lost 90% of your seed viability in the seed bank. But one individual can produce 300,000 to 500,000 seeds, right? So just one escape can sort of restart that problem. It's hopeful, right? So if we can suppress the populations for that long, then we can somewhat recover the ability to control them. So back to integrated weed management. So I want to talk just a bit about crop rotation, and this goes back to Carmen's work as well. Simplified rotations are going to be heavily dependent upon herbicides to control weeds and to maintain yields. There's really great work that has been done by Adam Davis, who of course is now at University of Illinois, but this was some of his work from 2012, where he looked at 2, 3, and 4 year rotations in an 8-year study in Iowa and saw that he was able to reduce herbicide use by 88% in the 3 and 4 year rotations compared to the 2-year rotation, while weed management was equivalent across all of those rotations. So crop rotation is the key to breaking pest cycles. And of course, we have to acknowledge that there is economic risk when we start diversifying rotations, because we're going to see ecological interactions that we don't anticipate. And this is one of the reasons that my lab has continued to work with industrial hemp for fiber. So we see that as a highly weed suppressant crop if you get it established. So just one crop like that in rotation in a summer annual cropping system could help us break pest cycles. So we're also doing quite a bit of work with cover crops, but intercrops as well. So I want to talk just a minute about that and the difference. So both of these will use resources in the times and the spaces when the crops do not, and they can preempt or replace weeds. Maintaining a living perennial ground cover between rows is one way to do this, and one way to potentially suppress weeds. But typically, if cover crops have to be terminated before we plant the cash crop. So one of the things that we wanted to look at with an intercrop or an interseeded crop now, this is not for yield, it's simply for weed suppression. So what is the potential impact on yield then if you have this this cover crop or this interseeded crop that's surviving at the same time now as your cash crop? So one of the focal points of my lab is also allelopathy. So we can think of this as just kind of chemical warfare between plants, where every plant or an allelopathic plant will produce plant secondary compounds that can have sort of an inhibitory effect on the growth of plants and microbes around them. So this is any secondary product that's produced by the plant. This can inhibit root and shoot growth, and these compounds can potentially be in all plant tissues above and below ground, but at certain points of a plant's life, it's going to invest more in one or the other often. But we can get these compounds from root exudates, leaf leachates, volatile compounds that are released from living plants, or compounds released from dead plants as they decay. And Johnson grass is a great example of this. Johnson grass produces allelopathic compounds, but so does Palmer amaranth. So I have a student that's studying the allelopathic effect of barley on Palmer, and I think that barley, we're about to do this with wheat as well, but I think that barley is going to be slightly more allelopathic than our typical wheat cultivars as well. So just to then now set the stage again, still talking about a potential interseeded wheat crop, I think we would see something similar to this. So PhD student Eduardo Lago has looked at both barley and cereal rye, and he has donor plants that he calls them, where he looks at the exudates of these plants and their inhibition on the growth of Palmer amaranth seedlings. He thinks that his hypothesis was barley would be better than cereal rye at reducing Palmer growth. And then he also had an hypothesis that if he exposed these donor plants to competition before he looked at their allelopathic production, then he would see enhanced allelopathy in response to competition. So these were his donor plants that he put in the greenhouse. So he would take an individual plant, he would wash the roots, and then he would put it into an auger-based system. But you can see for each species, either barley or cereal rye, he has that competing with or without Palmer amaranth. So then when he takes these, he washes them and he puts them in this auger-based plant box system. So it's a clear plastic box. And he seeds a grid of weeds across the top of the auger, and then he can clearly see the root and the shoot inhibition, and he can measure this as the allelochemicals move through that auger. So with this plant box system, he was able to show that you can see these are the root growth inhibitions and the shoot growth inhibitions on those columns on the right. He has the control plant that he's comparing to, so inhibition is a percentage of that. So he has cereal rye that significantly reduces inhibition or root and shoot growth. And then when he primes the cereal rye with Palmer amaranth competition, that inhibition increases. And barley, in his study, was by far the better suppressor, and especially when it was primed with competition ahead of time. So again, based on this work, we want to use these biochemical compounds of these species as potential additive effects in suppressing our amaranthus populations. So now to the basis of Madison's study a little bit more directly. This all came from an idea that was started in it was the mid-'80s with Dr. George Kapusta at Southern Illinois University. So Dr. Kapusta worked with a student, Paul Myers, to look at, here the title of his thesis, The Influence of Duration of Annual Grass Interference on Broadleaf Weeds in Soybeans. So they used giant foxtail, and they let the giant foxtail grow, then they planted soybeans into the giant foxtail, and then they terminated the giant foxtail with a grass-specific herbicide. Now, if I stood in front of you and told you to let your giant foxtail grow and then plant your soybeans into it, you would laugh at me. So this was a great opportunity to take something else that's domesticated, like wheat, that we're comfortable with, and use that instead of giant foxtail. So they did find that foxtail was effective at reducing the emergence and biomass production of broadleaf weeds, such as red root pigweed and soybean. And they reported no yield loss when adequate soil moisture was available early in the growing season. So of course, soil moisture is going to be the key to all of this. And then they decided that relying on a uniform stand of a natural grass is not a reliable practice at a commercial scale. So interseeding a grass species would be better and result in a more uniform cover. So that brings us back to wheat. And then, there was a study in 1996 that tried the same thing with spring planted cereal rye, and they found that it also worked just as well for suppressing, but it all really comes back to the moisture availability. If you go through a drought, if there's any dry spell, then all of these things, you're going to see a yield loss. So Madison's project here was a continuation of this, and we worked on this with Ronald Krause, who was the farm director at the Belleville Research Center. He had already looked at the difference in broadcast versus drilled wheat, and he found that when he broadcast the wheat seeds, he got much better coverage than drilling. So broadcast seeds got much better suppression, but then he had to do something to get good seed to soil contact, right? So that's how we move forward with Madison's project. Our winter wheat was broadcast into the system. But we were asking questions like, when does the winter wheat need to be planted to achieve the greatest water hemp suppression? When does the winter wheat need to be terminated to avoid yield loss? And is there enhanced common water hemp control when we overlay a residual herbicide over the top of an interseeded winter wheat crop? And is there an increase in soybean seed quality, which I won't talk to you about. That was a discussion that we just had. We saw significant results in one of our studies, but not across all of them. So I'm not going to tell you about the seed quality work. But you can kind of see the difference here. So on the left, you see our interseeded wheat system, where we have wheat and we planted soybeans into it. And then on the right, where we have no wheat, you can see the weeds between the soybean rows. So why winter wheat? Well, it's a familiar crop. It's easily terminated. If you use bin-run wheat, it's going to be low in cost, and it's not a weed. So it's something that we're familiar with. It's domesticated. We can manage it, and we can use it for suppression, for competition with other weeds, and to preempt those other weeds. So we had, for the bulk of Madison's research, we did this at SIU sites, the ARC, the Agronomic Research Center, the Horticultural Research Center in Jackson County. And then we also did some of her work at the Belleville Research Center in Belleville, Illinois. And then she had some trial locations for her SARE grant that were in Redbud, Illinois, Salem, Illinois, and Washington, Indiana. So I want to tell you about these 3 chapters of her dissertation. So I'll tell you about the influence of interseeded winter wheat planting date and herbicide programs on common water hemp suppression and how that impacts yield. And then the influence of interseeded winter wheat termination date on soybean development and yield. So when do you plant and when do you terminate? And then finally, I want to end with the SARE study where we were looking at refining these practices on farm at a large commercial scale. So for the planting date study, we wanted to identify the planting dates where we maximize suppression of water hemp. Amata is it's a code that we use for water hemp. And we wanted to evaluate herbicide programs on water hemp control in an interseeded system. And then finally, we wanted to see what effect that has on yield, most importantly, right? So these were our treatments. We had a fall planting, right? So fall planting is not desirable for this type of system. If you're going to double crop, then that makes sense, right? But we wanted a comparison. So we went ahead and put in a fall planting date. Really what we were looking at is when we plant in April, before soybean planting, early May with soybean planting, mid to late May, and, early May, yeah, and then no wheat planting where we have soybean only as our conventional comparison. So all interseeded treatments were compared to this soybean only comparison. So we had winter wheat plus soybean in most of our treatments, but then we had subplot treatments where we had a non-treated, so we had no herbicides to compare to. And then we had a weed-free, so the lab manually removed the weeds, so we were hand-hoeing weeds in that treatment. And then we had a post-only treatment, and then we compared all of that to the conventional pre followed by post, so the typical herbicide program that would be recommended. So some more of the details. It's a bit wordy, but I didn't want to forget to tell you these things. So soybeans were planted in late May, not in early May. So soybeans were planted in all plots at the time of the final winter wheat planting, and that was in late May. Winter wheat that was planted in October was desiccated, and that was at Feeks growth stage 10.5 in April. So keep that in mind too, because you would expect higher biomass, but we desiccated that winter wheat well ahead of soybean planting in April. And then the weed management treatments were, so we used for our post glyphosate and dicamba at that time. We used our pre was fomeciphen, esmetolochlor, which is prefix, and then we followed that with glyphosate and dicamba post. We used then hand weeding as a treatment, and then we had a weedy check where we did basically no weed management to compare to. So our pre-herbicide treatment was applied the day of soybean planting. So winter wheat that was planted at the late May planting date either failed to emerge altogether or the emergence was really reduced because of that herbicide treatment. And then naturally emerged weedy grass was not removed from the plots where winter wheat was competing. So it would have been impossible for us to effectively weed out the weedy grass. So keep that in mind too. You're looking at the effects of wheat plus any weedy grass that was there. So we saw, as you would expect, the dry biomass decreased across our treatments. If we plant in in April, that yielded the greatest biomass. Then an early May planting, and then October, right? And remember, we desiccated our October planted wheat in April, so that's why the biomass is that much lower on this graph. And then our mid to late May planting, along with soybeans, where our winter wheat did not emerge well at that soybean planting date, so the biomass is low. And then finally, soybean only, where we had no biomass. What you see there is any weeds that had emerged. And then you can compare 2020 to 2021 there. So now I want to show you, this is just for our BRC site in Belleville. This was the water hemp biomass 0 days after the post. So at that post-emergence herbicide application, this is the result of the suppression of the winter wheat. So we have weedy check in the burgundy bars, our post only, so that's in the blue bars, and then our traditional pre followed by post treatment, so that's the herbicide treatment that we're comparing to. The point that I want to make here is that you can see the water hemp biomass is especially low in these April plantings, right? So to us, that seems to be the optimal time if you want to use wheat, spring planted wheat, to suppress water hemp, then you'd be looking for the first chance you can get into the field to broadcast wheat seed in April. And you'd be ready to plant soybeans into that at a later date. This is important because that gives the wheat a chance to grow a little bit and to collect some biomass, and that's the key to suppression, right? So it needs to grow and take up the space and cover the soil. Now, this, of course, this is what you're all wondering, I'm sure, how did that impact soybean yield? So we have yield, it's presented in kilograms per hectare, but we have, again, the burgundy bars are our weedy check. The blue are the hand-weeded treatments, the gray post only, and then we're comparing all of that to our pre followed by post treatment. our traditional soybean treatment there. So 2020, you can see the weedy check had a major effect on yield. Our hand-weeded treatments also, I mean, I would like to say hand-weeded treatments always look good in science, right? But the truth is, you're going into the plot, you're hoeing out the weeds, and you're often accidentally damaging the crop as you're doing that. And just the fact entering the plots and walking around in the crop field, that often has an effect. So hand-weeded treatments should always look the best in science, but they often don't. So that's what we see here as well. Our hand-weeded treatments are lower in yield, but if you compare that post-only to the pre followed by post, that's really what we want to look at, because post-only means that the winter wheat is doing the job of suppressing, not the pre-emergence herbicide. So we're looking for cases where those bars are not significantly different. We have a bit of a difference in, you can see our early May, right? So we have a significant difference. So we do lose a little bit of yield, but this is in 2020. If we look, 2021 was a year with much better moisture. So we actually see, in many cases, we have no significant differences between our post-only and our pre-followed by post treatments. So this just supports the previous research that shows this is a viable system if you have sufficient soil moisture in these early stages, right? So it's all about the soil moisture available and what your crop has available. So in summary, when we used interseeding without herbicides, we were able to reduce water hemp counts by 83% in fall plantings, 81% in April plantings, 12% in early May plantings, and 14% in late May plantings still, compared to our soybean-only comparison. So we do see winter wheat doing quite a bit of the work there. And then we could see common water hemp biomass reduced. So we saw 78% reduction in fall plantings, 94% in April, 30% in early May, and 37% in late May when compared with soybean only. And then planting winter wheat earlier in the spring in April gave us the most consistent winter wheat biomass production. And in some instances, planting winter wheat in April ahead of soybean planting did reduce soybean grain yield compared to the soybean-only standard. Again, those were the years with low moisture. And then we saw yield reductions in the April planted treatment compared to the soybean-only pre followed by post-treatment, which was our standard comparison. And that was upwards of a minus 27% when herbicides were applied, and then a minus 82% when no herbicides were applied. However, in the same treatment, we saw that soybean grain yield was also as high as 28% over the soybean-only standard comparison. So we see this variability, and it really comes down to the weather and the precipitation events within the growing season. When do we see losses? And when, in this case, we did see a greater gain in the interseeded wheat treatment in some cases. So in our termination date study, we wanted to know, we now figured out when would be the best to plant. So when would be the best to terminate so that we don't lose yield? So we're looking at the optimal termination timing so that yield isn't negatively influenced. And I won't show you the data, but we looked at protein to oil content in our interseeded treatments compared to the soybean-only treatments. So here's our treatment list. So we had termination, our post-emergence applications at soybean growth stage V2 through V6, and then we had a weed-free non-treated, and we also had a soybean-only comparison, pre followed by post. So winter wheat was planted at the time of soybean planting, and the herbicide treatments, again, included our post of glyphosate plus dicamba. We had a pre of Authority first plus dual magnum, and that was again followed by a post of glyphosate plus dicamba, and then we had our hand-weeded winter wheat or soybean-only kept weed-free. And as you would imagine, when you wait later to terminate the winter wheat, you get a greater amount of biomass. So you see that somewhat consistently over the years. It's not a perfect curve. But then when we looked at the yield data, and I'll show you this for 2019. So this is yield comparisons at V2 and V3. So what I want to point out is that V2, we don't see significance in differences in yield between soybean-only and interseeded treatments. Same for V3 in 2019. And we're comparing that as well to our pre followed by post on the far right there, so our conventional or traditional approach to weed management. So even though the bars are quantitatively lower, statistically there's no significant difference. And then if we look in 2020, where there was, again, much greater moisture availability, the only real difference we see here is in the hand-weeded treatment where we have interseeding. So again, if you have enough moisture, you can potentially get good suppression and avoid any yield impacts. And the same in 2021, again, another year with sufficient moisture. We again only see a major decrease when we look at our interseeded treatment and our hand-weeded treatment. So depends on the year. And then if we compare, here's the rainfall data for 2019 and 2020. You see in the black bar there, that's our precipitation normals. We had in 2019, we had, you see a little bit of a dip in the fall there, but sufficient rainfall amounts, but we had even greater rainfall in 2020 and in 2021 during those early parts of the growing season. So terminating winter wheat by V3 could avoid significant grain reduction. And then when we see increased moisture during the season, during soybean reproductive stage, we could wait to terminate as late as V6, and that didn't result in any impacts to yield. So the use of residual herbicides in the post-emergent application did not always result in better end-of-season common water hemp control. So we saw in some cases that winter wheat can be just as effective as a pre-emergence herbicide. I wouldn't recommend that you leave out the pre necessarily, but in this case, it could be equivalent. So on-farm trials then, SARE gave us the opportunity to work with farmers on this. So this was incredibly valuable, and as you know as well, for a PhD student like Madison, there aren't a lot of options for students to be able to actually get their own grant and manage their own grant. So this was an amazing opportunity for a student to have to manage a grant. And our objectives here were to evaluate these practices across Southern Illinois and Indiana. We wanted to look at various interseeding implementation methods, and then we wanted to evaluate the effect of intercropping winter wheat on soybean quality across Southern Illinois and Indiana. So this was a large-scale field study that was conducted in 2021 across 3 locations. We planted winter wheat at 3.7 million seeds per hectare at each location. And the farmers used their own methods and their own implements to do this work. And that was the key to this proposal, right? We gave them the objectives and asked them, okay, given the tools on your farm, how would you accomplish this? So we had 3 treatments, soybean only, which was pre-followed by post weed control, and then soybean only, post only, and then soybean plus wheat post only. So again, comparing wheat to that pre-emergence herbicide option. So I want to quickly go through the different farms. So Decker Farms, which yes, was Madison's family farm in Indiana. Wheat was drop spread into vertical tilled ground and incorporated with a drill in April. And then they used XtendFlex soybeans. They applied their pre also in April, and they used Warrant Ultra. And then they applied the post 1 to all treatments, so glufosinate plus glyphosate. And then they did use another post, so they cleaned up their fields again with glufosinate plus glyphosate. So I want to show you that these are counts for water hemp, heights for water hemp, and then we see 2 separate counts for post 1 and post 2. So the key, you see post-only bar is burgundy, pre-followed by post is that conventional treatment, and then we are comparing all of that to the suppressive ability of wheat. So we see that wheat for counts, wheat is just as good statistically as our pre-followed by post in water hemp suppression. But if you look at this second chart here on the right, this is pretty significant here. So not only are our counts statistically equivalent, but our plants are shorter. So for someone relying on an herbicide system, this buys you more time to make an on-label application of herbicide. And that's when you have competition with a living wheat plant, right? So again, going back to those allelopathic properties and wheat's ability to compete and suppress, it's slowing the growth of the water hemp plants. So Hunter Farms in Salem, Illinois, they drilled wheat, again in early April. They used Enlist soybeans. They applied a pre of Warrant Ultra in late May, and then they applied a post to all treatments on June 22nd, and that was 2,4-D plus clethodim. So again, Hunter Farms, these are counts and heights. Again, you see the same trends where wheat actually reduces counts in this case, but not statistically different from pre followed by post. And then you see that wheat statistically, that's a significant difference there. So wheat has again reduced the height of water hemp in that treatment. And then the final farm, so Redbud, Illinois, wheat was drop spread and incorporated with the Phoenix harrow to establish their stand. They planted Liberty Link soybeans. They applied their pre on April 22nd, and that was Warrant Ultra. And then they used a post of glufosinate. And here they had 3 posts. Second post was glufosinate plus clethodim, and then post 3 was glufosinate. So again, you see same story. This is a little different here, counts for post 2. You see counts here are significantly lower and not different than pre followed by post. Counts for post 2 are a little different here, so we see the conventional program perform better. And then same with heights though. So if you look at heights, you have much more time to make an on-label application. And again, you see the third post there, the counts that are different. So Madison was able to publish her work with growers. So this is it's not a peer-reviewed publication. The SARE study was not designed in a statistical way so that we could publish it in peer-reviewed literature. So she's working on publications for her other dissertation chapters, but this is already out if you want to read about our work with SARE. So just in summary, kind of an overview. So we had these large-scale on-farm trials that reduced the height and the number of emerged common water hemp and Palmer amaranth. When we looked at the height of the 2 amaranthus species in the soybean-only, post-emergence-only treatment prior to post, the pre-program and the interseeded program were very similar, and both had a 91% reduction in weed counts. But then when we were observing weed heights, the pre-emergent herbicide reduced weed height by 48%, while the interseeded treatments reduced weed heights by 69%. So that suggests that when we interseed winter wheat, and when that wheat is properly established, that can extend the time to make an on-label herbicide application. And then implementation of the interseeded system did not reduce efficacy of the interseeded winter wheat program. So it didn't matter what method the farmers used to introduce winter wheat. Everyone successfully was able to implement the program. And then we didn't see a difference in soybean grain yield at any location in the on-farm trials, so I didn't present yield data. So the data that we have suggest that when implemented successfully, interseeding winter wheat into soybean can be an effective integrated weed management strategy for suppressing amaranthus species. So Madison had a lot of ideas to take this work forward. So how can we more effectively, introduce winter wheat in these spring applications? Can we maximize our effects by, using the same pass for multiple activities? And then with her preliminary data from her dissertation, we were able to get funding from the United Soybean Board, and we have this now across 8 participating states. And we're getting ready to hopefully get that analyzed and wrapped up and published as well.